All right, today we're going to try and decode the language of the universe itself. We're talking about physics and measurements. And look, I know what you might be thinking, but trust me, this is not your high school science class. This is the fundamental toolkit, the how-to guide for understanding literally everything, from why an apple falls from a tree to how an entire galaxy gets formed.
I mean, just look around you for a second. The universe is, well, it's a whirlwind of activity, right? From the way a planet spins to the fizz in your soda, it can all seem impossibly complex, maybe even a little chaotic. So the big question is, how on earth do we even begin to make sense of all of it? How do we find the order in all that chaos?
Well, it's actually pretty simple when you think about it. We learn its language. And yeah, the language of the universe is physics. It's a language that's built on observation, on being super precise, and on a set of rules that, get this, apply absolutely everywhere. So let's dive in and start with the basics. Okay, so our first step in learning this new language, we've got to understand what it's even about. What exactly is physics? So at its very core, physics is the study of two things: matter, which is basically all the stuff in the universe, and energy, which is what gives that stuff the ability to, well, to do things. But here's where the real magic happens. It's all about how they interact with each other. It's really the ultimate story of cause and effect, and it plays out on every single scale you can possibly imagine.
For instance, think about the study of motion. We call it mechanics. Simple questions like, why does a ball fall down instead of up? Or how does a planet manage to stay in its orbit? Yep, that's physics. But then we can zoom way, way in. It's also the study of the incredibly small. I'm talking about the world of atoms, the fundamental building blocks of everything you see around you right now. What holds them together? What happens when they split apart? That's also physics. And of course, we can zoom all the way out to the unimaginably large, the birth and death of stars, galaxies colliding with each other. I mean, from the absolute tiniest quark to the largest supercluster of galaxies, it is all governed by the exact same elegant set of rules. And that right there is the power and, honestly, the beauty of physics.
So if we're sticking with this idea that physics is a language, then measurement, well, that's its vocabulary. Think about it. You can't describe the world accurately if you don't have the right words, right? And in the language of physics, those words have a name. They're called physical quantities. So these words in our new language are what we call physical quantities. And it's a really simple idea, actually. If you can measure it, it's a physical quantity. Things like length, time, temperature, speed, these are the basic nouns and adjectives we use to build sentences that describe the universe.
And these quantities, they're the absolute fundamental building blocks for how we describe the world. I mean, stop and think about it for a sec. We use these concepts every single day without even realizing it. Mass, temperature, speed, pressure. What physics does is just take these ideas that we're already familiar with and give them super precise universal definitions. That way, scientists all over the world can be sure they're speaking the exact same language.
And you know what? Every single one of these words follows a simple two-part grammar. First, you have a number, which we call the magnitude. That's just the how much. And then you have a name, which is the unit. That's the of what. Just saying the temperature is 30 is totally meaningless, right? Is that 30 degrees Celsius, Fahrenheit, Kelvin? That unit is every bit as important as the number itself.
Okay, so we've got our vocabulary, the quantities, and our basic grammar, the number and the unit. But sometimes just saying how much isn't the whole story. Sometimes we also need to know which way. And this brings us to a really crucial distinction in physics, the difference between scalars and vectors.
And the difference between them is actually beautifully simple. A scalar is a measurement that only needs a magnitude, a number and a unit. That's it. A vector, on the other hand, needs all of that plus a direction. Now, that might sound like a tiny little difference, but trust me, it has absolutely huge implications for describing the world accurately.
Let's take temperature. It's a perfect example of a scalar. If I tell you it's 30 degrees Celsius outside, you've got all the information you need. You'd never ask, oh, 30 degrees Celsius in which direction? The question itself sounds ridiculous, right? It just doesn't make any sense.
But now, let's talk about velocity. That's a vector. And this example shows you exactly why that matters. If I tell you there's a storm moving at 10 kilometers per hour, what's your very next question going to be? In which direction? Is it coming towards us or is it moving away from us? That piece of directional info, east for example, is absolutely critical. It's literally the difference between having a nice day and needing to run for cover. All right, so we've established that units are essential. But here's the thing. For scientists all around the globe to be able to talk to each other and understand each other, they all need to be using the same units. We have to have a universal standard.
Because historically, this whole situation was just a complete mess. I mean, you had all these different systems all over the world. You had the MKS system, the CGS system, the FPS or imperial system that some places still use. It was basically like everyone was speaking a different dialect of the same language. It made working together really difficult and super prone to errors. Just try to imagine building a space probe when one team is measuring in meters and the other team is using feet. It's a recipe for disaster. So, to fix all this, the global scientific community finally came together and agreed on one single standard system, the Système International, or as we call it, SI units. And here is the truly amazing part. Every single physical quantity that we can measure, I mean, everything, from the speed of light to the air pressure in your tires, it can all be built from just these 7 fundamental base units. It's like creating an entire language with only 7 letters. That elegance is what makes clear, mistake-free communication possible for scientists no matter where they are on Earth.
Okay, so we've built this beautiful, elegant system, right? A whole language to describe the universe, complete with a standardized vocabulary and grammar. It sounds perfect. But there's one last, kind of humbling truth we have to face, and that is, no measurement is ever truly perfect. So now we have to talk about the reality of error. Now, it's super important to understand that when scientists say error, they don't mean a mistake. It's not about somebody being wrong. An error in physics is just the unavoidable little gap between our measurement and the true actual value of whatever we're measuring. Every ruler, every scale, every single clock has its limits. An error is just us being honest and acknowledging those limits.
And we can actually break these errors down into different types. First, you've got random errors. These are just tiny, unpredictable variations in your readings. Then there are systematic errors. These are consistent errors that often come from a piece of equipment that's a little bit off. You know, like a bathroom scale that always says you're 1 kilogram heavier than you really are. And then, well, then there are blunders. Okay, yeah, those are just plain old mistakes, like reading the number on the dial wrong. The whole game in good science is to understand and try to minimize those first 2.
And all of this leaves us with a final, pretty profound question to think about. If every single measurement we ever make has some amount of error, some uncertainty baked into it, does that mean we can never perfectly know reality? Are we always just looking at a slightly blurry picture of the universe? It's a question that really gets to the heart of what science is all about, that constant, ongoing quest to bring that picture into sharper and sharper focus. Thanks so much for exploring this with me today.